G'day, Doug Williams here. Welcome to this workshop on engineering aha moments in number. Actually, this is a starter workshop. The limits of technology mean that to get the best from the session, you'll need to follow up later using the links that I'll show you to Mathematics Centre and Calculating Changes. This is Mathematics Centre. I have it in full screen view. You can see the tabs up here, and that we are at mathematicscentre.com. All our work today in this session comes from Calculating Changes, which is this link on the left-hand side in our column of professional learning links. We take that one, and the home page for Calculating Changes looks like this. We will return here several times during the session. This is a polyplug set. Yellow and blue plugs, red plugs, and the plastic bag is part of the equipment. At the end, the children can hold up the bag, show you both sides. If everything's there, there's no gaps, so you've got the lot. Doesn't matter how they're in there. Let's have a look. Saving the bag over here for pack up. We have the red plugs and the yellow and blue plugs. And the first thing anyone wants to do, adult or child pretty much, is pop these things out and see what happens and play around with them and put them back in another way and so on. And that's wonderful because it's the attraction of the colour and the kinesthetic feel, the tactile nature of the resource that allows us to ask our first questions. Let's just move that one aside for a minute. How many blue plugs are showing? How do you know? Can you check it another way? Do you see another way if I turn the board around? How many ways could you find to convince me that there is, well, however many blue plugs there are showing? School mathematics is learning to work like a mathematician. And if you go back to the main page for a moment and scroll down a little, you'll find the Working Mathematically link. And in that link is a one-page description of what it means to work like a mathematician. And those questions we were just asking are from that framework. One of the ways to convince me is to use touch and tell. I think I can see a 6 here, and I know that because it's like on a dice. And there's 5 there, and I know that because I've seen that all of these rows are 5. And then there's a 3 there. So one way is 6 plus 5, which is 11, plus 3, which is 14. Another way might be, well, if it was around this way, 5 plus 4 is 9, plus 3 is 12, and 2 is 14. Now it's your turn. See if you can write 3 more ways to convince me that there are 14 blue plugs showing there. this doesn't happen in 5 minutes. I'm exploring some steps that can happen over time in the classroom. And it was you that I asked to write 3 other possibilities. And I don't know what you wrote, but I'm sure you want to tell somebody else and compare with them. In terms of asking students if they'd like to do this, that's the question. Not a compulsion to write, but the question, would you like to write down for me that one you just said? Touch and tell it for me and then write it down. So it may be that they write down something like this. 2 plus 3 plus 3 plus 6. Now, where do you think I was looking when I wrote that? It does equal 14. I was looking here and here, and then those 3, and that's 6. What do you think I'm doing, though, if I write this? Where did I look? Well, certainly this won't be the first thing that happens in your class when you're using these, but the children do soon come to realise that there are 25 plugs in a board. And the yellow ones have been taken out of the question because they're not blue. So 25 take away that 4, and then take away that 4, and then take away that 3, leaves all the blue plugs, and we know that's 14 for this board. So we're combining touch and tell with recording in a journal. At another appropriate moment, there's another question you can ask about the recording. Would you like to write that one you just told me on your calculator? Would they ever? And you can ask that question from the youngest class in the school. Yes, 5-year-olds. Last century, the Calculator Aware Number project in the UK, over several years with thousands of students and many hundreds of teachers, researched what happened when calculators were given to kids within a professional learning context for the teachers from the first year of school. The result was simply that over the period of time, children's number sense increased remarkably compared to what was expected for their age. Let's have a look in the background link and you'll see a little bit more. It's the reason why calculators and polyplug are the preferred equipment for calculating changes, and students are invited to use them as they wish, when they wish. It's the reason why teachers ask the children, how can we use the polyplug or how can we use the calculator to help us learn this? And it's the reason why we have a networking system to collect and share these classroom experiences, and you can share from that as well, with the objective to develop children's number sense beyond what is usually expected for their age. Further down this page is the Calculator Aware Number Project link. It's just a little bit of background there to start with, but it was last century, as you can see, the middle 1980s that began. And if you look in the second paragraph, you'll find that Victoria College, now called Deakin University, was able to repeat the results in Australia. There are several references to the report document throughout calculating changes. Further down still, book itself, the report book, suggests that children should always have a calculator available and a choice to use the calculator or some other method of calculation was to be the children's. They weren't going to teach traditional vertical pencil and paper methods, and that's certainly a point to be discussed, but it needs to be remembered in the context of research that it made a difference. Emphasis on good practice is what we've been looking at the moment. Many activities are not directly associated with calculators, but involving apparatus and materials. Developing confidence in talking about numbers, I've been hinting at that at the moment. Mental calculation and sharing mental strategies, and building brain pictures I've been looking at also at the moment. And they chose to make sure that number didn't occupy more than half of the curriculum. A little bit further down, you will find a couple of comments from teachers. First case, a head teacher, that the project had developed during its lifetime from initially being a calculator-based curriculum within number. It broadened out to take in, first of all of mathematics and then beyond mathematics itself, cross-curricular. And a teacher saying that she's constantly amazed at how much further on children are compared with following a traditional scheme. And so we know from 20 years of classroom research, a calculator is a valuable learning tool. A calculator used in conjunction with manipulatives is a better use of that learning tool, and a calculator used in conjunction with the manipulatives and an attitude, an atmosphere in the classroom that values children's efforts to learn is a powerful teaching package. So here's my calculator. I'll hold it there where I suspect you might be able to see it. And then we'll write the one that I just wrote a moment ago. 25, take away 4, take away 4, take away 3 equals 14. As I say, it doesn't all happen at once. I'm just trying to play out for you some of the possibilities that were in the minds of the calculating changes teachers as they developed their network. One more thing the calculator helps with at another time and another place, of course, is if somebody looks at that particular one and says, I know what I can see. There's 2 plus 3 plus 3 times 3. And they record it as 2 plus 3 plus 3 times 3. And we know that's 14. At worst, we could count it.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14. Would you like to record that on your calculator? Sure. Let's have a look. So we've got 2 plus 3 plus 3 times 3 equals what? 24? Ah, it's a machine, so it must be correct. It must be that there's 24 blue plugs showing. Huh? No chance. There's 25 in the board, so there'd only be one that was yellow if 24 was showing. Must have pressed the wrong button. Let's do it again. 2 plus 3 plus 3 times 3 equals 24 again. Ah, it must be this calculator. Maybe there's something wrong with it. I'll just use the one on my phone. Let me see what happens there. Okay. 2 plus 3 plus 3 times 3 equals 14. My calculator on the phone tells me there's 14 there, and I know it's 14. The calculator on my office desk tells me that there's 24 there, and I know it's not 24. What's happening here, please? And of course, this is an opportunity to begin discussing what is different, what is powerful, what should come first. Probably not with your first class in school, but it will come up somewhere. 10 Friends begins with the red board and pressing out 2 rows, adjacent rows of red plugs, which are stored in the plastic bag so they don't get lost. And we have the polyplug equivalent of a 10 frame. And we'll need 10 plugs to use in the game. We also need a dice. Somebody goes first, rolls the dice, and leaves the dice sitting where it lands. That doesn't move now until this round is over. And that same person then plugs in that many yellow into the board anywhere they like. And you'll see there's an obvious one-to-one correspondence situation going on here in terms of plugging in. And that person has finished their turn. The other person does not touch the dice and does not touch the plugs. The other person screws up their brow, thinks really hard, decides how many blue plugs they'll need to fill the gaps, and then says, I think I'll need 5 is perhaps the answer we'll get this time. And that's a hypothesis. And how is that hypothesis checked? Well, you count in the plugs, and they know that as well. So they go in 1, 5. Yes, hypothesis checked out. That's not the end of it though. This is a team thing, working together to complete the tens frame. perhaps a different way of using it from what you've seen before. And at this point, they've made something together. And together they say, and touch, look, we made 5 plus 5 equals 10. They know what the first number was because the dice hasn't moved. And they know what's added on because it's the other colour. When that's done, these plugs are taken out and they swap roles. Let's just do it once more. So this is the other player rolling now. And it's a 5. Okay, so it's a 5. So that player then plugs in 5. And they can plug them anywhere. So it's actually not going to look the same as it did before. Player B now looks really hard and says, I think I need, making a hypothesis just like a mathematician, and use the language. If a kid says, what's a hypothesis? What a great answer. That's an intelligent guess. That makes them feel good. Okay, makes the hypothesis, I think I need 5. 1. And together, what happens? Look, we've made 5 plus 5 equals 10. The feel of the game remains the same, but there's lots of opportunity from here. Would you like to write a number story for what you've made? Would you like to write that number story on your calculator? And you can expect that very soon someone's going to come to you and say, can we please play with 3 rows pushed out? You could say no, because the syllabus document says that you have to do numbers up to 10 at your age. But you could say yes, and then I guess you've got differentiation happening in the classroom automatically and by choice of the young people. But they will need to have some more plugs to do that, and you might even say at some point, would you like to do that 3-row game with 2 dice? Predict account is one of the most powerful activities I know. You have probably seen it in various forms before, but I doubt that you've seen this version unless you've been involved with calculating changes somewhere. It goes something like this. Kids, today we're going to teach our calculator to count forward from 0 by tens. So we'll put the 0 there as our start. We want to go forward by tens. What button should we press? Oh, we should press the plus and the 1 and the 0. Don't press equals. First, I want you to predict what will be on the screen if I let you press equals. Oh, we think it's going to be 10. Okay, let's put that down. How do we test that hypothesis? Yes, we have to press the equals. Let's see what happens. And equals is still on the screen. We got it right. Give it a tick. All right, we're going forwards from there. If we do plus 10, again, don't press the equals. What number do you predict will be on the screen? Okay, 20 you think. Let's write that down. And what do we have to do? Press the equals. It is 20. Give it a tick. Okay, next one. What do we have to do? We have to press the 1 and the 10. Okay. And what don't we press? Don't press equals. Because why? Because first we have to predict what will be on the screen. Right, we predict 30 and we get 30. We've got a tick. Okay, next one. Press plus and 1 and 0. Do we press equals? No, we don't press equals yet. What do? We predict what's going to be on the screen. Okay, what do we predict? We predict 50. Okay, terrific. What do we do to test that hypothesis? We press equals. 40. Oh, all right. Put a line through it and write what the calculator says. All right, so we got up to 40. Of course it is. 30 and 10 makes 40. We got excited. So we press plus 10 from there, and we don't press equals. We predict what comes next, and we think it's going to be 50 for sure, because if it was 30 and 40, the next one's got to be 50. And we press equals, and it is 50. We get the tick. And we keep going from there. It's going to be plus 10, predict, check the prediction, correct, plus 10, predict, check the prediction, predict. Got excited? No, but I will this time. Yay! Plus 10. What do you think it'll be? I think it's going to be this one next. Hooray! Let's see if it is. Yes! And what will be the next one? Plus 10. I know. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200! Hooray! Check the prediction. Huh?
This starter session is about to end and the real workshop opportunity is about to begin. After this session, I encourage you to make time to try predict account for yourself. Use any starting point and add or subtract any number. For example, mine might be Calculating Changes has developed a library of rich activities like these, but more importantly, teachers have developed a unique way of using them. We have called it threading because, for example, you use an activity for 10 minutes or so, 3 or 4 times a week, for 3 or 4 weeks, and in that way, it is threaded through the fabric of the curriculum. Threading is important in successfully engineering aha moments in number. If this session has interested you, then I also encourage you to research threading on site. There is a link to that section from 10 Friends, or Predict Account, and almost every other activity. You will also find it in the In Brief link on the Calculating Changes homepage. When there is a library of threaded activities available, building a workstation-style classroom in which children move through several activities in a session is very easy, and your planning lasts for several days. This concept, combined with investigations to extend the program across other areas of maths, is the basic structure of working mathematically with infants. You can find out more about this from the link on the homepage. It includes a sample planner from the manual that lays out 10 weeks' work for Year 1. So in summary, this is how Calculating Changes professional development helps you engineer aha moments in number. Feel free to contact me at any time with questions, comments, or contributions. Finally, here's 3 questions which might help you review this session. See ya!